This is Magban by Georgie and taking, of course, BS Ed Math section 2A. And here's my topic. Integral calculus area between curves. The area between two curves in a context such as the one in the question is literally that you have two functions, each of which has been plotted as a curve in a Cartesian plane with the horizontal axis appropriately labeled so that it is the input variable of both functions. If that variable is t and t, then the area between the two curves from AA to BB means you drew vertical lines. T equal AT equal A and T equal B, T equal B, and now the two curves and the two lines enclose a region in the plane and we measure the area of this region. But people also use the phrase area between the curves as a kind of verbal metaphor and or graphical shorthand for a definite integral of the difference of two functions. The basis of this metaphor is that in many cases, we can compute the area bounded by the graphs of two functions and by two vertical lines by taking a definite integral of the difference of those two functions. The problem with the metaphor is that if we integrate f of t minus g of t, f of t minus g of t over an interval on which f of t is sometimes less than g of t, we end up the regions of the plane whose area has to be subtracted from the total area in order to have the area come out equal to the integral. In the first case, we want to determine the area between y is equal to f of x, y equal f of x, and y equal g of x equal y g of x on the interval a, b, and a, b. We are also going to assume that f of x greater than equal g of x, f of x greater than equal g of x. Take a look at the following sketch to get an idea of what we're initially going to look at. In the area and volume formulas section of the extracts chapter, we derive the following formula for the area in this case. The second case is almost identical to the first case. Here, we are going to determine the area between x is equal to f of y, x is equal f of equal f of y, and x is equal g of y, x is equal g of y in the interval c d c d, with f of y is greater than g of x, f of y is greater than equal g of y. In this case, the formula is a is e. The formula is, you will see the formula by this picture. Next, examples. Determine the area of the region enclosed by y is equal to x of x2, y equal x2, and y equal square root of y equals x. First of all, just what do we mean by area enclosed by? This means that the region we're interested in must have one of the two curves on every boundary of the region. So here is a graph of the two functions with the enclosed region shaded. This one. this one. From this graph, it's clear that the upper function will be dependent on the range of x that we use. Because of this, you should always sketch of a graph of the region. Without a sketch, it's often easy to mistake which of the two functions is the larger. In this case, most would probably say that y equal x2y equal x2 is the upper function, and they would be right for the vast majority of the x-axis. However, in this case, it is the lower of the two functions. So, the integral that we'll need to compute find the area is this one. You will see the area is this one. Next, example 2. Determine the area of the region bounded by y equal xe minus x2y equal xe minus x2, y equal x plus 1, y equals x plus 1, x equal 2x equal 2, and the y-axis. Here, unlike the first example, the two curves don't meet. Instead, we rely on two vertical lines to bound the left and the right side of the region as we noted above. There are a couple of important things to note. First, in almost all of these problems, a graph is pretty much required. Often the bounding region, which will give the limits of integration, is difficult to determine without a graph. Also, it can often be difficult to determine which of the function is the upper function and which is the lower function without a graph. This is especially true in cases like the last example, where the answer to that question actually depended upon the range of xx that we were using. Finally, unlike the area under a curve that we looked at in the previous chapter, the area between two curves will always be positive. If we get a negative number or zero, we can be sure that we've made a mistake somewhere and will need to go back and find it. Note as well that sometimes instead of seeing region enclosed by, we will see region bounded by. They mean the same thing. And that would be all. Thank you for watching.